This is going to be AP Calculus, Unit 3, Lesson 4. We are still on graphical analysis. Today we're talking about when a function is concave up, when a function is concave down, and where the inflection points, the IP, are for our function. All right, so we have the setup for our notes. So I just want to talk about some notation really quick, and then we can knock these down. So a function is concave up. Obviously, that means f is concave up for our notation here. And now to fill this in, what does this mean? So concave up, what does that have to do with the second derivative? I'm going to do this in a different color so that I don't get my double quotes mixed up with my f double prime. This means that f double prime is what? Positive, exactly. F double prime is positive. All right, so what do I know about concave down? F double prime is what? Negative.
And then F double prime equals 0.
Ooh, that's a good guess. That was what I thought first, so that's perfect. You're thinking exactly like I was. But it's slightly different, and it's related to our notes from last week.
Does not exist.
No.
Close.
Or it's
That was a good guess.
Um,
But it's not just 0, but that it goes through 0. Do you remember what the difference is?
Is greater than or equal to. It's
No?
less than or equal to.
I'll,
wait, don't.
don't give it to you?
May I just say
Do we know it?
No. It's just kind of based off of some other stuff. So this is a sign change. F double prime sign change. Okay, I can spell here. S-I-G-N, sign change. So the second derivative changes its sign. And that can happen at two different points. Where can f double prime have a sign change? There's only two different things that can have a sign change. Yes, so you have the right idea. Those are the two types. But where can that happen? Where f double prime equals this, or where this happens?
where it equals 0?
Where it equals 0 is one of them,
Yeah, it doesn't exist.
or it doesn't exist, exactly. When it doesn't exist, it can just magically jump somewhere else.
What's wrong?
All right, so
Did you fall? Please tell me you did.
let's go ahead and label these. So this is going to be a graph of f, graph of f prime, and a graph of f double prime. And then I can put a little box around these, little rectangle.
So Sindel, I have a question.
Yes.
Calculus always about graphs? Is that what makes it calculus? Like I know like algebra is kind of like about.
So that's not the best way to think of it, because graphs are just another form of what we do. So I would say, in general, calculus is about the study of change. Algebra is about the study of how numbers are manipulated. Calculus uses algebra and then talks about how to study change,
Okay. Which involves a lot of graphs.
which involves a lot of graphs and a lot of equations and a lot of antiderivatives and a bunch of other stuff. But graphs are what this whole unit is about right now. All right, so let's go ahead and make a graph. I want to do a positive cubic. Do we remember what a positive cubic looks like?
It's a smiley face.
Cubic.
Oh.
There's a peak and a valley. Does it go peak first or valley first?
Peak. Valley.
Peak.
So remember, graph, if I want a positive cubic, it generally wants to be like this, but cubic. So it's going to start down here and end up here. So here's my positive cubic. All right.
So do we just have to memorize that, or is there like some way to?
You don't have to memorize it. It's just good to know. It helps you out because if I know I have a positive cubic, then the derivative of that, the graph of f prime, will be what type of graph?
Good question. Quadratic.
Quadratic and positive. Yeah, exactly. So quadratic means it's a smiley face, that U shape. And it's positive. It's the U shape, not an N shape or a rainbow. And then the derivative of a positive quadratic turns into what type of graph? Linear? What type of linear? Positive or negative? Yeah, positive linear. So I'm going to go right through the origin this time. I'm actually going to use my line tool to make sure I get a beautiful line
Does
here.
it matter if we go straight through the origin? Or?
For this one, it kind of does now. Actually, it has already mattered, but I just didn't catch it. All right, so I'm going to do my best to get sure. Well, this graph could have been better. I would have liked the inflection point to be exactly at 0. That way, at 0 throughout here, it would be perfect. I can retry drawing that cubic if you would like. Maybe I can do that while you guys are drawing it right now. Ooh, oh, my eraser's just lagging behind. Come on, come on. Oh, that's dust on my monitor? No, that's an actual line. Oh my gosh. Erasing. My computer's just so laggy. I'm trying.
What are you doing?
I'm trying to make this a better graph. Still is going to be a positive cubic.
Perfect.
Yours is probably going to be better than mine still.
Oh.
I'm trying to erase it. My computer cannot handle the stress of erasing and taking video at the same time. Oh well, good enough. All
I
right.
think it's a line.
So I want to try making this come up. I'm going to sketch this. And then come down through here. And then come up again. That looks better. All right, so I did the same graph, I just made it a little bit better. So we have a graph of f, f prime, and f double prime. So where is my inflection point? So again, f double prime has a sign change. So it's easiest to see in the graph of f double prime. Do you see where it changes sign from a negative double prime to a positive double prime?
Yeah, it crosses the x-axis.
Yeah, exactly. It's right there. So right here, we can label that IP, inflection point. The point of inflection. All right. All right, so that's what it looks like on a graph of f double prime, so memorize it. It's where it crosses the x-axis, or sometimes it's where it doesn't
Can we
exist.
write that below IP equals where?
If you'd like, I can write that down here. So, IP, since all of this is talking about IP, I guess for now, we can say, well, I'll just say it down. IP in this graph is cross x-axis, I can't speak, cross,
Just kidding.
cross x-axis. Okay, what about in the graph of f prime? What is f double prime? Is that height, slope, concavity?
It's height.
It's height.
I thought it was
Height.
slope.
I hear
No,
many
it's
people
slope.
saying
No, it's
height, a
slope.
few people saying slope.
It's slope.
Are you sure?
Yeah.
Not sure.
Why is it slope?
No.
It's height.
It's height because it's f prime.
I'm looking for f double prime.
So slope then.
So
It is slope.
yes.
Because slope,
It
you're...
always goes height.
Everyone was like
slope,
changing back.
Yeah, that's a good way to think about it. Those are the orders. Another way to think about it is that slope is when you take the derivative of that function. If I take the derivative of a derivative, I get the double derivative, or f double prime. So slope here is going to be f double prime. So I need to figure out where f double prime has a sign change. So where is IP in this one? Where is the
Can there be
inflection
two
point?
IPs?
There can be, yep.
It's on the
In this
bottom.
graph, there's only going to be one.
It's on the bottom.
It's on the bottom, right here.
Oh yeah, where it changes.
You're correct, but let's analyze why.
Wait, I thought it was where it crosses the x-axis.
That's only in the graph of f double prime.
Oh.
Which is heights, right?
The only thing that you need to memorize here is it's where f double prime has a sign change. F double prime in this graph is going to be slope. So here the slope is negative. Here the slope is positive. I change from a negative to a positive, therefore right at that intersection where it changes is IP. Let's label that IP. So IP here is where the slopes change from positive to negative. Slope from positive to negative. Or sorry, this one was negative to positive. Let me undo that. Slope was from negative into a positive. It's where it changed. And this is the same thing. It's the height change from a negative to a positive. Maybe I can write that below here too. Height changed, or I shouldn't do an arrow yet. Height went from a negative to a positive. All right. So what now? Graph of f double prime. Where is graph of f double prime in the graph of f? Where is it hiding? Concavity, exactly. So right here it's concave down. Right here it's concave up. And a good way of estimating about where it is you take where the slope is 0, and then find the midpoint, which right here, that's the midpoint between those two x values. And that's only roughly in a graph. If we had an exact equation, then we could tell exactly where it was. But just for a graph, that's a good way to estimate. So right here is the inflection point. Why is that an inflection point? What about our definition are we allowed to use?
It changes from
A
positive
sign change.
to negative, or negative to positive.
What changed from negative to positive?
Concavity.
Exactly. So IP here, so this was IP at that point, and it's an IP because concavity. I don't know why I wrote PB.
PB and J?
I'm just hungry right now, I guess.
Smells so good right now.
IP. This is,
I think writing talk.
come on, I can write an equal sign. This is where
Wish.
concavity went from a negative to a positive.
Is there ever going to be a graph of f where it starts as a valley and goes to a hill?
Starts at a value and goes to a hill?
No, valley.
Valley and goes to a hill? Yeah, so for a negative cubic.
Oh, okay.
Yeah, good question. All right, so we know where this function is concave up and down, so we have those two down already. Right now we're really dealing with inflection points. All right, you guys want to try another example?
Yeah, I'm having trouble remembering like when you remember its slope or height.
Okay,
The
so
way I think about it is like you're always looking for f double prime, and then like it just changes based on if you're on the graph of f or like the graph of f. Like it moves downward. Like I don't know that. That's just
so that's one way to memorize it, and I can give you another one too. You can choose whatever one you'd like. But whenever I'm given the graph of f prime, I know that in order to move to f double prime, this is basically what Kaylin said, I need to go one down, one derivative. The derivative is no longer height, the derivative is slope. From here I need to do double derivative, so I start at height, and then I go to slope, and then the next derivative is concavity, and I'm just looking at concavity for f double prime. Every time you go down a level, you go from height to slope to concavity.
Okay.
All right, let's look at some other graphs. So I want to actually,
So examples.
so some more examples, exactly. I want to do 3 more graphs. I'm going to put them right about there. 1, 2, and 3.
How much notes is there going to be?
We're basically going to do the same thing. We're going to label these a little bit more, though, to make sure we have it down.
But like, how much more after this?
So we're going to stop right about there. This is the last slide for sure. All right, so I'm going to say, again, this is going to be the graph of f, the graph of f prime, and this one is going to be, I'm going to put it over here, graph of f double prime. And I should probably have boxes around them. Black boxes would be better. Graph of f prime, and graph of f double prime. All right, so I'm just going to give you random graphs now. They're not going to be the same equation that I take the derivative of. I'm just giving you random ones back to back to back. So the first one that I want to do is a positive quadratic. So a positive quadratic, that looks like this. Trying my best to sketch it. And I'm actually going to give us values here so that we can analyze it more. So this is going to be -1 for that x-coordinate, and this x-coordinate is going to be 4. For the graph of f prime, maybe I should have done g prime since it's technically a different equation. I want to do a negative quadratic. So a negative quadratic looks like a rainbow. And again, this x coordinate, let's make this something different, -3, and we can make this something different as well. Oh, we can do the same thing. Let's do 4. And let's try finally we'll do like a negative absolute value. So I can do 2 lines here. So we'll say it goes down like this and down like this. Perfect. All right. And we can make this 5 and 1. Or sorry, 1 and 5. All right, so I need us to label where f is concave up, where f is concave down, and where the inflection point is. So let's label these f, concave up. You'll give me some interval. You're going to tell me where f is concave down. Again, tell me some interval of x values, and where the inflection point is. It'll probably be x equals this point. And we're going to be doing this over and over again. So I'm going to copy and paste this.
We can't do that on our notes.
Yeah, thanks, Mr. Sandor.
You're welcome. Bless you. Right about there. Cool. All right, and that's as much as we're writing in our notes. We can stop right there. All right, so do we have everything copied down here?
Yeah.
Almost.
Almost. I'll give us a few seconds to make sure we have the setup, and then we can knock them down. All right, so f concave up. For this first graph, where is it concave up? For what x values is it concave up?
And that's when it goes from negative to positive.
So it would be, which
So-
notation do you want?
So concavity is determined by, again, our definition, where f double prime is positive.
Between -1 and 4.
So between -1 and 4 is our first idea. You can either
Yeah.
agree or...
So x is greater than -1, less than 4.
Okay, so you're agreeing that that should be the interval, that it's concave up?
Yeah. No,
Okay.
down.
You're saying it's concave down for that interval?
Yeah.
All right.
Wait, I thought
Remember that we're dealing with the graph of f here.
Oh.
So you have to go down twice. The first derivative, well first, if I just take heights, I'm looking at what? Heights will be
Infinite, or height, sorry.
f prime, or f double prime?
Prime.
No.
Double prime.
Heights are whatever this value is
Just
here.
clear that.
So heights are f. Heights in this one are going to be f prime. Heights of this one are going to be f double prime. So heights are f. What are going to be, how do I find f prime? What is that going to be?
Slope?
F prime will be slope, exactly, and f double prime will be
Concavity.
concavity. So where is this?
I'm just going through all of
Now we just have to remember concavity. Concavity means we are seeing if this is a, and we can make a note over here too for concavity. What? I don't know.
What the heck, Mr.
It wasn't me, I swear. So concavity, for the graph of f, this is where it's going to be a rainbow or a smile. So we'll say smile or rainbow.
Oh, it's a smile the whole time.
Smile is positive, rainbow is negative concavity. You can say concave up, concave down. All right, so where is this concave up?
Infinity.
Everywhere. Yeah, so you can say from negative infinity to positive infinity. It is concave up everywhere.
Okay.
Say that again, Troy.
Wait,
Down doesn't exist.
Yeah, it's never concave down.
Wait, I thought that was talking about height though.
So concavity is the second derivative.
Oh.
Second derivative means we're just...
So confusing.
Me too.
This is always concave up.
So we're talking about, like, we're not talking about heights at all right now, we're just talking about concavity?
We're talking about concavity. But concavity looks different for each type of graph. All right, so for the graph of f, it's concave up at all values. Where is it concave down?
Doesn't exist.
Yeah, you can do a line there, you can say DNE, you can say none. I'm fine with any of these. As long as you know that it is never concave down, that's what I'm looking for. This is always going to be a smiley face.
So there's no change, so there's no IP.
Exactly, yeah, no change, no IP. You can put nothing there.
Nice, Rosalie.
All right, but now we're looking at a graph of f prime for our second example.
Concave up would not exist, right?
So, again, let's look at the definition of what it means to be concave up. F double prime is greater than 0. The second derivative is greater than 0. The second derivative is now going to be what? Heights, concavity, is it going to be? It's going to be slope. So we see that concave, it's slope positive there, slope is negative there. So where is it concave up? Remember, concave up is f double prime is greater than 0.
So
Is it
negative
positive?
infinity to negative 3.
What?
Negative infinity to negative, or positive, right?
I'm so confused.
So where does it change from a positive slope to a negative slope?
Right in the middle of them, between -3 and 4.
Yeah, somewhere right here.
Which
Well,
is
let's
7.
let's assume that that's 1 or something. It's technically 0.5 if it was a perfect quadratic, I think. Let's assume that it's 1. That means it's concave up between, or it's has positive slopes for this line. This line has positive slopes between negative infinity all the way to 1, which means f double prime has positive values between negative infinity and 1. If I'm given the graph of f prime, f double prime is going to be slopes.
Wait, I thought it went height, slope, concavity.
It does.
So then how do we get...
So right now, I guess concavity is a bad word here. F concave up doesn't mean where is it concave up. It means where is f double prime greater than 0. So you're looking for f double prime.
So it's not really concavity.
No, that's kind of a misnomer. I mean, it is concavity if I reduce it all the way back to the graph of f, but now that I'm looking at the graph of f prime, that's probably going to confuse us.
Okay, but I thought that on the graph of f, f double prime was slope.
You're right. So where is the slope greater than 0? Where is slope positive?
No, but I thought that was
From
on the graph of
-3
f,
to
not
1?
on the graph of f prime.
Sorry, f double prime is not slope on this one. So right here, this is f prime. F double prime, okay, I need to color code this because otherwise it's going to get too confusing.
It's already confusing.
If I do slope here, this is f prime. If I do concavity here, this is going to be f double prime.
Slopes, no, it's like-
Now if I do heights here,
No, I meant
Graph of f is going to be concavity.
right. And then
if I do heights here, heights are going to be whatever I'm given. Heights are f prime. Slopes are now f double prime.
You want to find, you always want to find double prime. So f double prime is concavity.
Okay, I get that. So then on the graph of f, wouldn't it be that f is height and f double prime is... Oh, f prime is slope.
Yes,
F double prime is slope.
exactly.
Okay.
Yeah. Yeah. So then for this one, the graph of f prime, we're looking for the interval where it's positive on the slope, right?
Exactly.
Okay.
And where is that?
Between -3 and 1.
Close, because I would agree that it's -3 and or at 1, But what about negative 4?
So then it's just negative infinity.
Yeah, negative infinity. All the way to 1, not including 1. This question is asking us, where does this function have positive slopes? This function has, or where does this line, because technically the function is here, but this line of f prime, it has positive slopes from negative infinity all the way to 1. Positive slope, positive slope, positive slope, all the way down here. It'll still have a really big positive slope if I extended the graph all the way down here. F concave down is where do I have a negative slope?
1 to negative. No, positive.
Exactly, 1 to positive infinity. Because again, we're just going back to the definition. Where is f double prime negative now? F double prime is slope. This is f, come on now. This is f double prime. So this is concave down. Because I'm given the graph of f prime, it's concave down from 1 to infinity. The slopes are negative between 1 and infinity. Even smaller slope, even smaller slope, even a more negative slope. The slopes are always negative as long as I'm to the right of this point. Are we getting this? Nods heads? Okay. So where's the inflection point then?
1.
All right, so at x equals 1. Because that's where it changes between a positive slope and a negative slope, or from a negative to a positive if we looked at a different graph.
I feel like my problem is that like I get it now when you're explaining, and like I get it when I'm doing my homework and I have the answer key like to help me explain it. But then like when I get to the test and I just see it, like that's when I get confused.
All right, I understand that we have worries about the test. I'll do my best to make sure when we go through all of the self-checks that we treat it like the test and really analyze what's going on.
It's just that, like, when we get to the test, then, like, I see the problem and, like, I don't think, oh, yeah, this one's the one to do, like, concave up or whatever.
Yeah.
You know what I mean? Like, I know how to do it once they're like, oh, well, you do this. And I'm like, oh, okay, I remember that.
Okay?
You know what I mean?
I think that's just going to come to us with more and more practice. We'll get there. I promise. All right, let's look at the graph of f double prime. What am I looking for now? Before I was looking at concavity, then I was looking at slopes. What do you think we're going to be looking at now for f double prime? Height, exactly. Heights here are going to be f double prime. So where is it concave up? Where do I have what type of heights?
From 1 until 5.
From 1 to 5, exactly. And what about concave down? There's going to be 2 intervals here.
Infinity to 1.
From negative infinity to 1?
Oh, yeah.
And where else?
From 5 to infinity.
From 5 to infinity. Perfect. Because those are negative heights. You guys got it. And inflection point, where are they?
1 and 5.
X equals 1, x equals 5. So really, everything that we're doing here came from our definition. This is the most important thing that we were doing today. Concave up means f double prime is greater than 0. Concave down, f double prime is negative. IP, inflection point, f double prime has a sign change.
Wait, I don't get how the IP is from 5 to infinity.
Sorry, IP, this right here is talking about where it's concave down.
Oh.
Inflection point is where x equals 1 and x equals 5.
Oh, okay, that makes sense.
Where it crosses the x-axis, where it has a height of
So then
0.
how come for the concave down there's 2 different ones?
Because concave down is where I have negative heights. And there are 2 intervals where I have negative heights.
I get it. Okay.
Negative heights there and there. All right, that concludes our notes. Let's go ahead and write some summaries.